Good day, everyone. Our topic is all about the multi-flow problem. From the definition, we have multi-flow concerns the transportation in a network in which various types of products must be transported from their sources to specific destinations. Each road has some transportation capacity, and there are increased demands associated with each pair of source to destination. The network that connects sources to destinations may be modeled by the theory of graphs, like a transportation network. The multi-flow problem is a generalization of the flow problem which deals with a case of one type of product, one source, and one destination. Okay, multi-flow problem. No? For the simpler definition, we have transportation in a network in which various types of products, several types of products that needs to be transported from their sources to the specific destinations. Multi-flow problem could be we can get this through maximal flow and a minimum flow. It could be a maximum flow or a minimum flow. For the maximal flow, these terms we need to remember: source, sink, range above the network and range below the network, and then the cut. Okay, later we will illustrate that one. Let's proceed to the max flow minimum cut theorem. A cut may be defined as any set of directed arcs containing at least one arc from every directed path from the source to the sink. There are many ways to slice through a network to form a cut to help analyze the network. For any particular cut, the cut value is the sum of the arc capacities of the arcs or in a specified direction of the cut. Okay, remember the definition of the cut value, the cut, and then we have the max flow minimum cut theorem states that for any network with a single source and sink, the maximum feasible flow from the source to the sink equals the minimum cut value for all cuts of the network. Thus, if we let F denote the amount of flow from the source to the sink for any feasible flow pattern, the value of any cut provides an upper bound to F, and the smallest of the cut values is equal to the maximum value of F. Therefore, if a cut whose value equals the value of F currently obtained by the solution procedure can be found in the original network, the current flow pattern must be optimal. Eventually, optimality has been attained whenever there exists a cut in the residual network whose value is 0. Okay, we have the example. Find the maximum flow in the transport network using labeling procedure. Determine the corresponding minimum cut, 7 marks. Okay, we'll answer that later. Okay, so for now, we will going to discuss all the different terms and the definition that we've discussed earlier. Okay, if we have this network, okay, in this side, in the left side, we call this the source. This is the source. In the right side, the sink. And then, in this part, we have the range above the network. And this, in this side, we have the range below the network. Okay, now we will going to identify where is the cut in this network. So, the definition of the cut. A cut is the line that runs through the network from above to below the network. So, this above to below. So, this one is a cut. This one, a cut. We have this one is also a cut. Okay, so the rule of the cut is that we always cut from top to bottom. That's the important thing that we need to remember. If we're going to cut from top to bottom or above to below. Okay, so if we have this example, okay, we have to solve this one using the maximal flow. We have, okay, so from top to bottom, so we will start from this part, this one. Okay, so we can see that 3 is the minimum, so 3, so it will become 0, this one 0, and then 2. And then next, we have this part. So, we have here 2. So, this will become 0, and this will become 2. The next, we have this part, this one from here. Then we have the remaining 2, so this one. So, they are all 2. So, this will become 0, and this 0, this will become 0. Then, another way, if we will going to find, if we have the idea to the minimum cut, then we have this one. Okay, so we have here another network. We have here another example. So we have O, A, C, T, D, and B. Okay, to find the minimum cut, we have first 8 and 3. We have 11. And then 2, 4, and 2. We have 8. Another, we have this one. 4 and 3. We have 7. Okay, another one, we have, I guess, we have 4, 4 and 2. We have 6. Okay, is there any? So, we keep on looking for the minimum cut. So, we try to locate it from different networks. Okay, so we have, okay, yes, we have 2. We have 2 and 3. It is 5. So I guess that's also the minimum cut and is 5. And therefore this is the minimum cut, and therefore the maximum flow is this one, 5. Okay, proceed to another example. Okay, so we have here another example. It is more complex because we have much bigger capacities already. Okay, so we will start here. 750 and 680, we have 1,430. Next, we have 500, 200, and 400. We have 1,100. And then we have 370, 180, and 400. We have 1,150. And then we have 370, 90, and 650. We have still 1,100. And then for 400 and 650, we have 1,050. So we can see that the minimum cut is 1,050. So therefore, the maximum flow is this one, 1,050. Okay, so in this part, we will going to answer the problem na ganina dito sa tuang slide. Okay, so we have there the problem. It was stated that we need to find the maximum flow in the transport network using labeling procedure. Determine the corresponding minimum cut. Then it was in the 7 marks. So we have 7 marks: A, B, D, Z, E, and C. Okay, so to solve that one, we have first, we have to find, we have 2. We will to find the maximum flow and we will to find the minimum cut. Okay, we have this one. We have first from top, so we have A to B, B to D, D to Z. So we will write it here. A to B to D and to Z. Okay, so we have here the minimum 4. Okay, so this will become 0. This one will become 1. This one will become 5. Okay, so the flow here is 4. Okay, next we have A, B, E, and Z. So we have to write this one: A, B, E, and Z. So it is very important to have this, we can call this table, because it is very useful for us to locate, much easier for us to locate the maximum flow. Okay, so proceeding A, B, E, and Z. So we can see here that it is 4. Okay, so this will become 0, this will become 2, and this will become 1. Okay, this is it. So we have 4. Okay, before that, so this one 0, say black already, blocked. Okay, this one blocked also. Okay, next we have, okay, we locate A, C, E, and Z. So this one A to C, C to E, and E to Z. So we have to write A to C to E and to Z. Okay, so we can see here, okay, we have here 2. So yes, this will become 0. Then this one minus 2, we have 3. Then we have 6. Okay, so it is 2, so we will write this, the flow is 2. Next we have, okay, this will be blocked. Okay, so the only left here is A, C to Z. So we have A to C and to Z. So we can see here, so we have 3, so this will become 0, and then this one, so the remaining is 3. We have 3. So that's the end of our solution to find the maximal flow, because this one is already blocked. Block, 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 and block. So we cannot continue, so it will end. So we will going to total this one to get the maximum flow. 4 plus 4 plus 2 plus 3 is equal to 13. Okay, so we're done looking for the maximum flow. Now we are now on the minimum cut. Okay, so we have, set the edges whose removal divides networks into two values x and y, where x and y, where s we have here, where s belongs to x and t belongs to y. So diba, this in this side is our x and this side is our y. Okay, so we have, if you say for instance A, B, E, and C, this one is our x, and then D and Z is our y. Okay, so we have to remove. Okay, removed. We have removed B to D is equal to, we have B to D, we have 4. Next, C to Z, we have 3. We have 3. Okay, next, E to Z, we have we have here 6. This one is 6. Okay, the total of 4 plus 3 plus 6 is equal to 13. So we can see that the maximum flow and the minimum cut is the same. So we can conclude that capacity of cut is equal to the maximum, we have, this part is the maximum flow, so we have the maximum flow is equal to the capacity of the capacity of cat. Okay, so that's end on our discussion. I hope everyone understand. Thank you for listening.